Okay, good morning.
Good morning, sir.
My slides, you can see my slides?
Yes, sir.
Okay. All right, so let's get started. And so today, so we will be doing the powerhouse of deep learning, which is kind of training deep neural network using a particular very efficient algorithm, which is called backpropagation. Okay. And I told you last time that it's essentially stands on very simple calculus. Okay, just like high school calculus would be sufficient. Okay, from mathematical point of view. So just like chain rule of derivative is what we are going to apply here. But because today's modern deep neural networks are very big, that means that sometimes in billions of parameters. So you get to if you do not apply a very efficient algorithm, then there are going to be trouble. Okay. So
Hello.
yes, go ahead. Go ahead, please.
Hello, sir.
Yes, go ahead.
Sir, in condensed k-nearest neighbors, inside it for 1NN, can we use library?
Inside what?
Like for using 1NN, one nearest neighbor. Can we use library?
For 1 year, I mean, because this is the first assignment that I've given, I wanted you to kind of code it up. So please do not use any library there at least.
Okay, so for 1NN also we have to implement it.
Right. It's actually very simple, like a couple of lines of codes. So
Okay. Thank you.
All right. So yeah. So that's what we're actually going to do. So the purpose of this basically efficient computation of the gradients. Okay. You can do in a normal way, but we have to basically deal with very large network, lots of parameters, lots of data. So you need to have some efficient mechanism. But that is the only known, only well known, I would say, the technique which you'll use to train a deep neural network. So quickly, I will run through the components that we have been talking about, just to refresh your memory a little bit. So structure, there are a bunch of hidden layers with some number of neurons, one input layer, one output layer, and so on. And so you have, already how to set the number of neurons in input layer, number of neurons in the output layer, and the middle part is a little tricky. So you essentially figure it out that what would be the good configuration for that. Okay. So the things that we are interested in this particular algorithm backpropagation, we will be finding out the WLIJs and BLIs. So WLI, I mean, this is the notation I'm going to use throughout this particular presentation. And so if you carefully look at this, that WLIJ denotes that basically connecting layer from L to L plus 1 and the weights, their weights. Okay. Similarly, bias, I discussed yesterday, bias for every neurons which is not part of input layer. Okay, and you take a particular activation function. Okay. I also talked about how we actually compute the inputs and outputs in every neuron. So input is basically a linear combination of the signals or the values receiving from the previous layer, and output is going to be you apply activation function on that. Okay. So that is the kind of the basic fundamentals that we talked about. Okay. Now the question is, okay, now that given this particular network, okay, now when you basically you apply this network to do some kind of task, be it classification, regression, or whatever you want to do. Okay. So given the feature vectors, you basically take a feed forward pass. Okay, from first layer, you basically compute all the values. second layer, compute all the values, and basically this way you proceed. And finally, in the final layer, you are going to get some numbers, which is output, which you can basically term at class level, whatever. Okay. So, but in order to do all these things, you need to have these values, the W's and B's. You need to have that. Okay. Unless you have that, you cannot do anything because these are parameters in your model. Okay. So you have that. And so what would be the good values of those things? Because there are many possibilities. If you consider modern deep neural networks, they have billions of parameters, not in thousands, they're in billions actually. Okay. So what is the combination of these values, W1, B's and etc., that is going to give you a good performance on a particular task? For example, the recommendation task we had been dealing with. Or if you want to apply this, for example, credit card fraud, okay, you have some data and you want to figure out who is going to do some kind of fraud in future, or like text classification or image classification, lots of things basically you can do. But for every data, every problem, every data, you need to know that what would be the good values of these W's and B's. Unless you know that, you cannot do anything. Okay. So this purpose of this particular lecture is essentially to focus on that aspect, how you can efficiently compute the values, the W's and B's, so that you are going to have a good performance on a particular task. Okay. So that is what we are going to do in this particular tutorial. Okay. So let's start basically talking about this. So how we do this training deep neural network. Okay, and I will basically proceed with like simpler one and then gradually get into complex things. Okay, so that things are a little clear to you. Okay, so before I move on, so essentially I like to emphasize on this that this is not something magic box came out of like somewhere. Okay, there is some very strong rationale and fundamentals behind it, and it's actually an easy algorithm. Okay, if you carefully follow it. Okay, so the purpose of the main purpose, or perhaps the only purpose of this algorithm is to compute these gradients, the differentiation, these values. Okay, so given a network, I have to compute all the partial derivatives of all this, with respect to all these parameters. You remember that from your gradient descent. Okay, so I need to have those kinds of things. So purpose of these, the only purpose of this is basically how you can efficiently compute, very quickly compute those values. That's it, nothing else. Okay, and it's called backpropagation. And why this is backpropagation, you get to know why this is called backpropagation later on. Okay, all right. So before I move on, before I get into this neural network stuff, I would like to talk a little bit about backpropagation on a simple graph. So why graph? Because neural network is nothing but a graph structure. We have some values in the input layer. You are gradually computing these values in every layer and passing it through the next layer. Okay? So from left to right, we are proceeding this. So in a sense, this is a graph structure. Okay? So that's why it is called the graphical structure. The graphical model we will also call it. So I would like to first show you how you can compute this called a backpropagation, whatever you can call it, on a simple graph, which you can probably manage. Okay? And from this particular figure, you can very clearly see that the function that I'm dealing with is a 3-variable function, x, y, and z, and you can see this definition of this function, x plus y to z. Okay. Now, if I map this function, some graphical representation, for example, consistent with neural network, whatever that do, that it looks something like this on the right side. So you have 3 inputs, x, y, and z, basically three variables. And then first I compute x plus y in one node. Okay. Then what I get, intermediate thing, I take that, then basically I compute the product with z in another node, and finally I compute the final value. Okay, so that is, you can simply, if you manipulate these things, then you are going to get the functional expression that I have written down. Okay. Now let's see how we can actually compute the gradients on the simple graph first. Okay. So in order to do that, let's let me just. Okay. So what we are going to do is this. So I want to compute. So my values, for example, so the gradient as such doesn't have any meaning. So gradient at some point, particular point. Okay. So let's consider the point that I'm going to consider is this. So this is x equals to say -2, y is equals to 5, and z is equals to -4. Okay. And my end goal is basically at this particular point, I want to compute these three quantities: del f, del x, del f, del y, and del f, del z. Because I have three variables in this function, so I have to basically compute these three quantities. Okay, so that's what I want to do. Okay. Now, if you look at this expression carefully, then q here, this q is nothing but x plus y, because it's the intermediate computation is happening. Okay. So that's what basically we want to do. Now, what we do in a typical like network that I have basically, so once you have some values, you first take the forward pass. Okay. Forward pass means computing these values from the output values from every node. Okay. So if you take a forward pass with values x, y, and z, then the value of q is going to be here is 3. Okay. Similarly, if you do this thing, then value of f here going to be -12. Okay. So that's the forward pass we do. I mean, once, because we know why we have to compute the derivative. So here x, y, and z, -2, 5, and 4, -4. So I can basically take a forward pass. I can compute the output values from every node. That's what we do initially. This will forward pass. Okay. Now what we do? Now I know q equals to x plus y. So I can compute then. Okay. So then del q, del x at this particular point. So this point. Okay. This is going to be 1. Very straightforward. Similarly, del q, del y is going to be 1. Okay. Because I know this q is basically x plus y, so I can very easily compute those things. Okay. But my ultimate goal would be to compute del f, del x, del f, del y, del f, del z. All right. Now let's get into second phase. Okay. Now, so x is basically -2. I'm just writing down again the values. This -2, 5, and this -4. Q is equals to x plus y, and I know del q del x is 1, del q del y is also 1. So this is 3, this is 12, sorry, this is -12. Okay. Okay, all right. So now my AF is here is Q star Z. Because if you look at this expression, this is what basically I have computed. Okay. So now what I can do now, so del F del Q is equals to Z. Similarly, del F del Z is equals to Q. Okay. Now what? Now, because this, so what is del F del Q and del F del Z are doing? Okay. So they are actually computing the kind of, say the local derivatives. Okay. So del f del z and del f del q. So here, so del f del z, okay, you are computing this derivative with respect to this. So del f del z is going to be 3 here, okay. Similarly, del f del q is going to be minus 4 here, okay. So here basically you are doing this particular thing here, okay, and del f del z you are doing with respect to this particular link, okay. So in order to compute the derivative of all these things, you have to compute the derivative in every node. So in this case, there is only one intermediate node. So in order to find out del f del x or del f del y, then you need to know basically del f del q as well, okay. So these are the intermediate values that I am getting now. So then del f, what would be my del f and del y? So my del f del y would be, now remember that the chain, the path, in order to compute del f del y, I have to start from this link. I have to come all the way along this particular link and basically through this point. Okay, so this is basically a link I'm going to follow. So if I have to do that, then first I need to compute, because this f q is basically I'm feeding the value of q to f. So first I need to compute del f del q. Okay, if you simply follow this particular chain, and then what? Q depends on y. So then this is del q del y. Okay. Now because I have all the values, I know del f del q, I know del f del q del y and everything. So this is going to be minus 4. Okay. Now similarly, if I can follow the other thing, for example, I'm just writing down here. Say I have to compute del f del x, because I have to compute everything. So del f del x, again for del f del x also you can think about it. So similarly I am proceeding in this way, this path, following this path up to this one. Okay, so it is del f del q because it depends on this, and then del q del x. Okay, so this is going to be minus 4. Okay, so you can see from this figure now that I have got del f del x, del f del y, and I also had, I believe, del f del z. Okay, in this one. Okay, so in a sense, in deep neural network is nothing but a composition of function. In this case, what's the composition of function? You are giving some values x and y and z, whatever. Then you are computing this whole thing, another node called q, which is taking the addition of x plus y. So first composition. Then you are taking this value q with the z, the second composition. So in a sense, you can basically, so here I am basically doing two kind of composition. Composition means I am applying some kind of function on a particular input values. Okay. So if you remember, if you can recall the structure of deep neural network, so every layer you are basically doing that kind of compositions and passing along this value to the next layer. Okay. So in a sense, it's basically composition of functions, and as a result, you can actually apply this kind of rule, this kind of chain rule of derivative to compute these values. Okay. All right. So next, what we do, we do this thing like, back propagation on, I'm just keeping this part. I had some blank slide because if I needed to. Okay, now I'm coming to the actual network. Okay, so the network that I'm going to talk about is backpropagation on simple deep neural network. It's actual network, and I will basically use this particular network structure to tell you that how backpropagation actually works on a simple network. We try to understand, generalize this concept, and then we will take a bigger network and try to generalize even more. Okay. So let's say on the same chain rule of derivative we're going to apply, but in a efficient way we're going to do that. Okay. So let's have the structure ready for us. And because I'm dealing with a very simple network, so my network structure is going to be like this. Okay. I have one feature, say my data that I have, for example, I have only one feature, I have two class, and I have two hidden nodes in a neural network. So you know there is only one node which is yellow, which is input node, and two class. So because this is a two class problem, you can have only one output node, because if the value of the output node is close to 1, then this is one class. If it is close to 0, this is another class. So any two class kind of problem you can model using a single output node, single output neuron. That's what I'm doing here. Okay. Now the middle part, the number 1 and number 2 nodes are basically hidden nodes, and it's a very simple network, you know, only for one feature vector, one dimensional feature vector. Okay. So quickly fix some notations. So here the capital I denotes. So I mentioned that every node or every neuron will have some input and some output. Okay. So I denote this by I that input value to neuron I. Of course, except the input neuron. Okay, the yellow one. And then OI is basically output from a particular neuron. Okay, or node, whatever. And F is the activation function that you are applying from it on every neuron. Okay, so that's the notation that I'm going to use in this particular lecture. So let's do, so once you have the value, some value X, then you can basically proceed further and compute O3. That's not a problem. Okay, so that's the network that I'm going to basically train. And question that I have to address is basically how we can get values W1, W2, W3, B1, B2, and B3, so that for a data, my network is going to do very well, in the sense that this is going to predict most of the examples correctly. Okay, in the training data. That's what we want to do. Okay. So therefore here I1 is equals to W1 star X plus B1, the same rule that we discussed before. Okay, so weight into the value from the previous layer plus the bias. Similarly, O1 is going to be function, the activation function applied on that input value that we also discussed. Similarly, I2 is going to be what you are receiving from the previous layer, which is f of I1 in this case, multiplied by the weight W2 plus bias of the neuron 2, and then similarly O2 is going to be the activation function applied on I2. I3 is going to be again similar thing, the output value that you are receiving from the previous layer, which is f of I2 star the weight plus the bias, and O3 is going to be f of I3. Okay, so this is the way basically you are going to take the forward pass. Okay, for every sample you have to take the forward pass to compute the value of O3 for a particular configuration of W's and B's. Okay, and then you see how this is actually performing, comparing against the actual ground level, so on. So then let's see how you can do that. Okay, so up to this, anybody has any doubt, any question? Okay, so what we do next is this. Okay, all right. Now that I know that how I have to compute all these inputs and outputs and everything in the network, okay, I still do not know my values, the parameters. I can randomly initialize these things, but I do not know what are the good values. That's what I have to do. Okay. So what I do, so now that the most important thing is that we need an error or performance function, and I mentioned this during logistic regression or linear regression thing, that in supervised machine learning problem, in particular in parametric machine learning, supervised parametric machine learning problem, you need to have an error objective function. And the objective function is going to tell you that for a given configuration of the parameter values, okay, how this model is actually performing, because we do not know the parameter values, and you know all the time you have to initialize randomly and then you have to change these values, okay, to find out good performance, to make sure that your model is performing very well, okay. So you always randomly initialize these values in order to compute something, but that is not a guarantee that you are going to have good performance. So we need to have an error function, a performance function, which will guide us, tell us how well my current parameter values are actually doing on the training data. Okay. So what can be an error function in this case? Okay. So for different problems, you need to take the different error function. There are lots of error functions. We will also talk about those things later on. But what can be an error function in this case? Okay. So my error function in this case could be something like this squared error that we already discussed. Okay. So E is half O3 minus Y square, where this O3 is predicted by a neural network. So when you randomly initialize these values W's and B's and everything for a particular input sample, it is going to give some value O3. So O3 is basically predicted by your network. Okay. And the Y value is the gold standard or the true level. And this is coming from the training data. You remember the format of the training data. You had the input feature vectors and corresponding class level. Okay. Or what if you are dealing with regression, so output value. Okay, so that is coming from the training data, Y value. And so here I'm defining this error function, the squared error. My objective would be what would be the good values of W's and B's, weights and biases, so that my error is minimized. In this case, minimum error means the 0 in this case. Okay, so what would be that? Okay, and that is what basically I have to do. So here E is playing the role of the error function and the performance function. It will tell how well actually I am doing. Okay. We have to now deal with this E and compute the partial derivatives. Okay. All right. Now, now see what next we can do. So this is my error and performance function. I know that basically I have defined and this can guide me. Okay. Now the question is, how can I find good values of parameters? Because I have to minimize this error function with respect to these network parameters. There are 6 parameters in this network. 3 weights and 3 biases. Okay. So I have to basically, figure that out. What would be the good values of these things? Okay. So the technique that we learned so far is that given a smooth function, continuous function, okay, we can minimize you can minimize and maximize whatever. So if we want to minimize, we can minimize this using a thing called gradient descent. Okay. That's we have already discussed. The gradient descent is the right technique to be applied here. Okay. Okay. So all right. So if that is the case, then what we need actually to do that? So what is the gradient descent rule for a parameter say W1? So here we have 6 parameters and you have to compute this for all parameters. So let's focus on say parameter W1. So if you recall the gradient descent rule for a particular parameter W1, updating parameter W1, then it is going to be like this. So W1 new, the new value would be my old value minus learning rate R into daily del W1. Okay. Now this is my thing. So the question is here now that I have everything else apart from daily del W1. I know W1 old because I randomly initialize these values when I am going to start. I know the value of R. Okay. The only thing that I do not know is daily del W1. If I know daily del W1, then I can basically, I get my update rules. I can do that thing and going to update all my parameter values again and again. Okay. So the question is, how can I compute this quantity? del E del Wi, and that is the purpose of backpropagation. The entire purpose of backpropagation is to compute this thing. So del E del Wi is I for all the parameters that we have for all the weights and the biases. Okay, you can compute that. Now, before I move on to the next slide, one small remark is that you may probably something maybe crossing in your mind is that is this the gradient descent rule we are going to apply? I mentioned that people actually apply more sophisticated gradient descent rule like Adam or the Adagrad or things like that. But you know, in all Adam or Adagrad whatever, so the component that we use actually the gradient values, nothing else. We take the average of the gradients, some kind of average of gradients, but we use the gradient values. Okay, so in any case, the gradients are the building blocks for everything. Once you have that, you can compute these things. Okay, so we need to compute all the gradients. That's what we do. Okay, so yeah, okay, so that is the purpose next, that how we can compute all these gradients efficiently, and I am emphasizing this term efficiently. You can, with the normal technique, with your high school knowledge, high school calculus knowledge, you can compute the gradients for all these things in a complex function. Okay, and it is going to be exactly the same if we apply backpropagation. But backpropagation is giving you very, very efficient mechanism to compute these things. Okay, so the efficiency is the main reason that we basically appreciate backpropagation much more than anything else. Okay, all right. So let's see how we can do that. Okay, so let's compute gradients. So here I'm going to focus on few parameters, not all, and probably you can generalize these other things, you know, very easily. Okay. So now here what I'm trying to tell you is this, that my error function is here is E, and I have to compute del E del W1, for example, del E del W1, del E del W, del W3. So 3 weights, and then for all the biases as well. So let us focus on the weights. Okay. So here is what is happening. So I'm saying is something like this. If you look at this carefully, and probably internally, you know, there is a thing called, I always use this term, okay, that may be non-standard thing. So I always call this the influence diagram. Okay. So what is the influence diagram? And that basically, once the diagram is ready, then it helps you to figure out, okay, this chain rule of derivative much more conveniently. So what I need to do? I need to do basically, I need to compute the derivative E with respect to this one, this quantity with respect to W3. Okay, and I can basically quickly figure out this chain rule, because when you have a long chain, it may be difficult. So here is what I'm actually doing. My influence diagram is something like this. So see, E, okay, is getting influenced by O3, because value of E depends on O3. Okay, then O3 is getting influenced by I3. Okay, the input to node number 3. Then I3 is getting influenced by the parameter of my interest, which is W3. Okay, so W3 is influencing I3, I3 is influencing O3, O3 is influencing my error function. Okay, so that is the way the information is actually propagating. Okay, and because I have to compute daily del W3, so I only interested, you know, if I change a little bit of W3, okay, then what is the change in my error? That's what I'm going to measure, right, in this, using this derivative. So now straight away, just, you know, convert this whole thing in terms of this chain rule of derivative. So here for this, because E depends on O3, so this expression. Okay, now O3 depends on I3, so this expression. Then I3 depends on W3, then my this expression. Okay, so that is the way we can very sort of conveniently and easily compute the chain rule, or whatever the derivative of a particular with respect to particular parameter. Okay, now what would be my del E del W2 then? Okay, so if I compute del E del W2, in a similar fashion. Okay. So my daily del W2 is going to be something like this. So E depends on O3, O3 depends on I3, I3 depends on O2, O2 on I2, and I2 on W2. Okay, similar. If you kind of draw the influence diagram again, that should be very straightforward. All you have to remember is that if I change W2, the parameter that I'm interested in, how that W2 is going to influence, or how that W2 is basically, getting propagated in my network up to the output layer, the output node. Okay, so that's the thing that you have to remember. You can draw a very simple diagram and then straight away you can compute all this chain rule very conveniently. Okay. So I got del E del W2, and then what? I need to compute del E del W3. So in a similar fashion, I can compute del E del W1 actually. Yeah, because that's the leftmost weight parameter. Okay. So in a similar way, you can see that del E del W1. Okay. So you can see these values. Okay, now one final remark before I move on is that these are all derivatives, So but then actually I have to compute this expression, convert this derivative into expressions. So can somebody suggest what is the value of del E del O3 in this case? Del E del O3.
O3 plus Y.
Del E del O3, how much it would be?
O3 minus
O3Y. Very good. Okay. Now what would be the value of del O3, del I3? Can somebody suggest?
F dash I3.
F dash I3. Very good. Okay. Now what is the value of del I3, del W3?
F of I2.
O2.
O2, yeah.
Del I3, del W3?
O2.
It's O2?
Yes, sir.
Yeah, this is O2 because this is F of I2. Okay, so it's basically O2. You are right, yes. Okay. So therefore, from derivative to I have all these expressions ready. So I can simply compute daily derivative because I am randomly initializing these values. So initially I have all the values ready, W1, W2, W3, B1, B2, B3, whatever, all these parameters will be ready. So randomly, then I have this expression also ready. Okay, so then I can simply compute the derivative of daily del W3. Makes sense? Is anybody has any doubt on this? That's a fundamental. If you understand this, most of the things you will understand very easily.
Sir,
Yeah, go ahead.
do you compute that F prime I3, sir? Like that.
Oh, okay. I coming to that. Okay, so F prime I3. So I am putting this as generic form only because that the F is basically activation function. Okay, so you probably may need to change. I mean, you can basically play with tan H, sigmoid, this and that, and so on and so forth. Okay, so depending upon that, you have to compute these things. So, for example, if you take say something, I'm just giving you a simple example. If your activation function is something like this, say linear activation function, for example, then you can know that F dash I3 is basically 1 only. Now, if you take real U activation function, for real U, what happens? So F dash of x is 1 when you have x higher than 0. Okay, sorry. Let me just erase this. This is going to be problematic. Okay, so when you take real U, then F dash x is going to be is 1 when the value of x is greater than or equals to 0, and this is 0 elsewhere. Okay, so it depends on like what activation function you are taking. If you take sigmoid, you can straight away compute the derivative of sigmoid function. Because this is the univariate function, right? This is not multivariate. The activation function is an univariate function. Okay, because the input that it's receiving is basically a scalar quantity. So it's pretty straightforward. Okay, anybody has any other doubt? All right. So this way you can also compute daily del W2 as well. Same way you can just simplify this thing and you can compute this all the parameters. Okay, and for the biases I will leave it to you as a very small like exercise. You can do it later on. For the biases you can straight away compute this. Okay, so maybe you can try it out and then you can discuss in the next lecture about the expressions. Okay, now before I move on to the next slide, I have one small question for you. So question for you is, and this is probably will help you to do some kind of sanity check in case you make any mistake. Now I assume that this is the problem configuration that I have, that and take this kind of neural network, not very complex, so same linear kind of thing, so it's only one neuron everywhere. Okay, so say I have n hidden nodes or n hidden layer and everything else is same. Instead of 2 I have n. Okay, now can you tell me the number of expressions that you have in this? So number of expression means this.
+1.
Sorry,
n+1.
it would be
n plus
how many? You tell me. N plus 1 or n plus 2?
n+1.
Okay, what's the length of the chain that you have to basically manipulate?
The n hidden neurons and one output neuron.
Right. So expression means this. So for example, if you look at this particular example, so expression is the number of this derivative component in this.
2n plus 1.
2n plus 1.
2n plus 1?
Yes.
Okay, anything else? Okay, first answer was n plus 1, second was 2n plus 1. Okay, all right. But you can
Yes,
see.
sir. It would be 2n plus 1. We would also need to consider the biases.
2n plus 1. Okay, why 2n?
Sir, because we also have to consider the activation functions derivative also.
Okay, so can you verify that with your this expression whether it's actually valid? So in this case, you have two hidden nodes, two hidden neurons, and one output. So basically, you are saying that if it is so, then according to your formula, okay, it should be the number of expression for W1 should be 5.
Sir, it will be 2 into n plus 1 plus 1.
Yes, sir.
Okay, one more expression, 2 into n plus 1
Plus 1.
plus 1. Okay, is it like you can validate this with these things, right? You can get these things from here. Is anybody who is contesting this, like find any hole in this, that okay, this is not the right thing? Okay, now can you just tell me how you computed this one? Like why this is the case? 2 into n plus 1 plus 1. Why 2 into n plus 1 and then y plus 1 then?
So like for every hidden node there are two derivatives and
Right.
there is one fixed for the input. So that will be 2 times n plus 1 And for the output, it is fixed remain as 1. So.
Right. So when you are manipulating, when you are passing this information through every hidden neuron, then you are giving input, then getting output. So for those processes, you have two components. Okay, for every neuron, and finally you have, so total how many neurons? You have n hidden plus 1 output neurons, n plus 1. So 2 into n plus 1 for that, and plus finally 1 for this error function. Like so, error function depends on z. So for that you have only one more expression. So yes, you are right. So 2 into n plus 1 plus 1. Okay, so this is in a sense like when you are like maybe implementing or doing something, you can quickly validate that whether you are doing the right thing. Okay, so okay, all right. So this is the thing. Okay, now basically this is I'm telling you this is a high school calculus, nothing challenging in it. But then how backpropagation is helping in this? Okay, what is big deal in it? Okay, so big deal is this. Okay, is this. Let's try to understand this one. So here. This is chain rule of derivative, I'm just, everybody knows it. Okay, now, if you look at this, and I'm just copying these things from previous slide, same thing. Okay, now if you look at these things carefully, first take a look at the left part, the green highlighted part, okay, green colored. Now, when you're computing daily del W3, you have computed something. Okay, now I have all the expressions ready, daily del W3, daily del W2, daily del W1, so on and so forth. Now you look at these common parts between daily del W3 and daily del W2. There are two expressions common. Okay, in it. Similarly, if you look at the common parts between daily del W2 and daily del W1, there are four expressions common. Okay, four expressions are common. So these common parts, because you have these common parts, the trick in backpropagation is to use these common parts. Okay. So if you look at this expression very carefully, now I can basically, when I'm computing del E del W3, I'm computing the whole expression. Now next, when I'm going to compute del E del W2, then I also have some expression there which is common with del E del W3. So what I can do then, when I'm computing this expression, or the whole expression during del E del W3, I can basically save this particular thing with some variable, additional variable. Okay, say temporary variable, I say T1, for example. I'm basically storing that. Now, when I'm going to compute daily del W2, I do not need to compute this expression again because I'm saving these values into T1. Okay, so in a sense, this is going to be T1 into this expression, the whole expression. I don't need to compute this whole thing again. Okay, so basically in this way I'm going to minimize this computation. Now when the chain becomes longer, and which is the case for deep neural network because it's a very high depth. Okay, so in a sense the chain becomes very longer. Now you can see these common expressions here. There are four expressions common. So when you computed daily del W2, you can, for example, you can save this whole thing into another variable called T2. So when you're computing daily del W1, what you need to compute T2 into only this expression. Okay, that's what you do. So that is basically saving your time. Okay, and as you basically progress from right to left. Okay, then the length of this common part is very long because we are dealing with a very deep neural network. Okay, length is very long. Okay, this particular common chain. So therefore, you can actually reuse this value that you are computing from the previous computation directly into this framework and then compute this efficiently. Okay, so that is where the backpropagation comes into picture. Now, just quick question. Now, that's the reason that I have three gradients I have to compute with respect to W3, W2, and W1. Now, as a blind, like if I give it to the high school student, he should be able to do it. There is nothing challenging in it, but he won't be able to do in a particular order. The layman will probably first compute daily del W1, then daily del W2, and then del W3. Okay, so if you do that in that order from W1 to W3, you are never going to make use of these common parts. Every time you have to recompute it. So that's the reason. So therefore, we have to basically do it from the other way around, from right to left, so that I can make use of this common structure in my computation. Okay? And that is why it is called the back propagation. You are simply propagating from right to left. Okay? Smaller to the bigger one, and you can reuse it. So this is like a very popular, there's a framework in somebody who has studied computer algorithms, design and analysis of algorithm. There is a thing called dynamic programming. Okay? So this is essentially a dynamic programming thing. Dynamic programming. Okay? So what dynamic programming framework does, it basically stores the values, some values which will be used repeatedly again and again in a table. You compute once, you store these values into a table, okay, in tabular format, and then you use it whenever you need it. You don't have to recompute from scratch. Okay, and that is what's called dynamic programming. So there is a whole branch in computer science which deals with that. So backpropagation is a classic example of dynamic programming. Okay, so that's the way basically you can do it. Okay, so if you have any question, you can ask me, or else we're going to take a break and then we come back and then talk about the bigger network.
Sir?
Yes, go ahead, please.
Sir, so here you are basically saying that first we update W3 and then go to W1.
Okay, I think what you are trying to suggest is that, okay, so when you are updating W3, once you update this value, then when you're computing W2, whether you are going to use the updated value of W3. That's it, your question?
Yeah, yes, sir.
Generally, that is not the case. Okay, because there is some problem. Okay, so you basically you retain the old values actually. So the moment you update W1, W3, you do not use immediately updated W3 value in W2. You use the old value of W3. Okay.
Okay.
Yeah. Because if you do that, then whole lot of other computation you will have to do, and that's going to be very slow. So you basically do that.
Sir,
Yeah, go ahead.
so as we have computed the expressions for del E, del W3, del W2, so similarly we will do it for del E, del B3, B2,
Yeah,
D1, right?
exactly. And the same thing, yeah, same thing, yeah. Similar way, I mean, you just manipulate this expression. So the expression for del B1, B2, B3 are relatively simpler because you do not have this coefficient involved there. Okay. So for W3, you have this multiplication coefficient f of I2. So when you are computing for B3, that won't be there. So expression will be much more simpler. And you can try it out in a similar way. It's exactly the same. So for this network, you need to compute 6 partial derivatives, 3 for weights, 3 for biases. And that's it. Okay, any other question? All right, so we take a break and then we come back and then we discuss a bigger network, okay, much more realistic network, and we try to formalize this whole algorithm, okay, so that it is you can very easily implement it. Okay, all right. Okay. So let's try to generalize this for a bigger network. Okay. And so my purpose in this case is to give you a general algorithm or method for training any kind of neural network. Okay, it's like very compact form so that you can write couple of for loops and you basically done something like that. Okay, so far what we talked about, that we have seen there is a kind of this substructure in the sense that overlapping substructure in this problem. So when you are computing the gradients for a particular variable, a particular parameter, then the parameter next appearing next in the network is basically there are some common parts in it, and we basically have to leverage this structure efficiently in a compact way, and that's what basically I'm going to show you in this particular section. Okay. So quickly again, let's consider this network structure again. Like this is a relatively complex network structure, and you can very easily generalize from this one after this session, I hope. So quickly, just I will give you these notations again. Okay, general notations. So the topmost numbers, as you can see, is basically layer number. For convenience, I'm putting this. And WLIJ is basically the weight connecting neuron I to neuron J from one layer to next, from layer L to layer L plus 1. Okay. Similarly, BLI, the bias of neuron I of layer L, and ILI is basically the input to a particular neuron, ith neuron of Lth layer, and similarly OLI is the output from the ith neuron of Lth layer. So these notations will be very, very useful, and you can basically follow from this notation what it's actually doing. Okay, it's basically, it has some meaning. Now layers are numbered from left to right, you can see this, and in every layer the neurons are numbered from top to bottom. Okay, so the top neuron is 1, next is 2, next is 3, and so on and so forth. So this is the convention I'm going to follow in this particular section. Okay, and so it is very important to be able to interpret these meanings of these connections, the notations. Okay, when you are doing these things in complex network, so basically that is absolutely necessary. So make sure that you can quickly interpret what it is actually, and the way that I have chosen the names basically consistent with what I'm trying to do here. Okay, so never consider this L to be a power. It is basically layer number. Okay, not a power. Okay, some people confuse this, so please don't do that. All right, so I have the same thing now that I have two-dimensional feature vector, and basically I have one output and so on, but you can generalize these things for any kind of network. Okay, I'm going to show you the general structure of this. Okay, so with this, let's get started. Okay, so first thing that I will be asking from you is that what would be the value of ILI, capital I, L, small I? Okay, in terms of B's and W's and O's and what? Yeah, can somebody please suggest? Because in any case, I have to compute the I's and O's for every neurons in my network. So an ILI and OLI essentially is basically for all neurons in the network. So yeah, so that we need to have a general rule. So what would be that?
O,
Sorry, say again.
O top 1 I minus 1 plus O I minus 1.
So if I consider IELI, this is a general rule I'm asking for, and you can assume that this one.
Yes, sir. You have to
Yeah,
have the weight and the mass.
just one more expression. So I'm putting this in NL is basically N sub L is basically number of neurons in layer L. Okay, that's the another expression that I'm using. Small NL. You can basically use that. Small NL. Okay. Now yeah, please go ahead. What would be my expression for I, capital I, L, I? That is the input to the ith neuron of Lth layer.
Sigma of W into O.
Sigma, okay, I take sigma, then what?
W L minus 1.
W L minus 1, yes, of course.
Ji.
J into I.
Into O of L minus 1 J.
O of L minus 1 J.
J runs from 0 to
J runs from
0 to N L minus 1, I think.
0 or 1, because my indexing starting from 1.
Yes,
J
J
runs
equal
from
to
1
1.
to 2, sir.
1 to N.
L minus 1, I think.
Okay. Is that everything that I need?
Plus P of L minus 1.
Plus the bias term, right?
P of L.
P of L of what? I.
I.
Okay, all right. Yeah, that's correct. Now, what would be my OLI?
F of I L.
Okay. So F is the activation function, Activation function. Is anybody has any objection on this? Okay, because this is kind of general rule that we are going to apply in this whole network. It's important that you understand this one. So you apply these things to compute. In any case, when you have a sample, when you're doing a forward pass to compute the predicted value, then you have to do all these things. So compute all the values from left to right. Okay. I hope nobody has any doubt on this. All right. So let's move on. Okay. Now that I know how to compute all these inputs and outputs and everything, now what next? Okay. That's the first step. My second step is going to be this. So I just copied these expressions on the top right. You can see that this expression that I copied for your convenience so that you can refer to it whenever necessary. Okay. All right. So next, let's basically start with a small one and then we'll try to generalize the whole thing. Okay. So let's try to compute by the way, how many parameters you have in this model?
2.
2. How can be 2?
Sir, by parameters you mean features or?
The model parameters, these neural network parameters, which you are going to basically train, find it out.
N of 0.
Sorry, what?
N of 0, right?
N of 0.
Sorry, N of 1. N of 1.
12 maybe.
18.
Well, how many weights you have here?
Like 4 for each, 1 layer to layer and 2 at the last, so 18.
But total, how many total number of parameters you have in this model?
24.
18 plus 5 biases also.
So it's a 16 plus 18. 18. There are 18 weights, right? There are 18 weights, isn't it?
Yes, sir.
Yeah. And then how many biases you have?
5.
5. Why 5?
6.
Why 6?
Like 1 for each layer.
But you have. I think it is 9.
9. Sorry, 9.
Right? So 18 weights and 9 biases. You do not have any biases simply the input layer. So all else will have their own biases. Okay.
So that become 11, right? Then.
So 18 plus 7, sorry, 18 plus 9 is 27.
So like there are 5 layers and then one output node, right? So 5 cross 2 plus 1.
No, I'm talking about the number of parameters. Parameters means parameters in absolute term. How many W's and how many B's you have total?
Sir, it is actually NL minus 1 into NL plus NL minus 1, including the biases.
Repeat again, N into?
Means for going from layer L minus 1 to layer
No,
L.
yeah, I think you are suggesting the general rule for that, but I'm asking for this particular network.
Okay.
For this particular network, what is the number of parameters you have?
Yes, sir, it's 27.
It's 27 because there are 18 weights, right? From layer 1 to layer 2, you have 4.
Sir,
Yeah,
So
go ahead.
like there are
sir,
5
input, starting input, won't it be a parameter?
How can the input be parameter? Inputs are basically known to you.
Okay.
You're probably missing the main thing. So see, you are given a training sample. So in a training sample, what are things known to you? The feature vectors known to you,
Yes,
and
sir.
the output label known to you. So the x1 and x2, they are basically the values already known to you. They are not parameters.
Okay, got it.
Parameters are the thing that you have to figure out from this model, and this basically weights and biases.
Okay, sir.
Okay, I
So,
think, yeah, go ahead.
so from layer 5 to layer 6, there would be 2 weights also, right?
Yeah, 2 weights. Yeah, absolutely. Yes, that's correct.
So there would be 20 weights, right?
Sir, including that 200, it was 18, right?
Well, I think you are probably missing something. Okay, so from layer 1 to layer 2, how many parameters, weight parameters you have?
4.
4. So then the next layer 4, next layer 4, next layer 4, 16. And then in final connection between 5 to 6, there are 2. So 16 plus 2 is 18. Isn't it? So there are 18 weights. You disagree or agree with me?
Agree.
Okay. Now how many biases you have here?
9 bias.
9 biases, because for the input layer you do not have any bias. There are 9 biases. So 18 plus 9 is 27. So 27 parameters you have in this model, or in this network. Okay. All right. So yeah, any question from anybody? Okay. All right. Okay. So let's take a specific weight and try to compute this derivative using this complex network, and then we will generalize the whole thing. Okay. Okay. All right. So let's talk about this weight, for example. Which one I should take? Okay, let me take this one. What is this weight of this? What's the name of this weight? In terms of W?
W23.
W2 of 1, 1.
W2 of
1, 1.
So I am going to compute this one, del E by del W2 1, 1. Okay, because this is the connection I'm referring to. By my arrow, the blue colored arrow that I just put, that is what basically, now that's the weight, and I'm going to compute this one. And we will basically generalize this whole thing. Okay, I hope everybody is on the same page with me on that. Okay, I do not know yet my E, so I will define E now. E is the error function. So again, let's focus on the same E that we are taking. So my E is equals to the squared error I am taking. So this is Z minus Y whole square. Y is the gold standard coming from the training data. Don't confuse, okay, between this y and z. Z is given by my network, is a predicted level, and just 1 minute. Okay, so Z is given by the network. So when you have a sample, you have the feature vectors, you take a forward pass, and then the Z is going to be that value if you take the forward pass. Okay, but Y is the actual level for that sample that you have in your data. Okay, so for clarity, let me just explain this because there is some confusion, I believe. So your training data is in this form. Your training data have in this form. Let me just. Okay, so training data that you have in this form, for example, in this case, something like this. Say you have x1, you have x2, and you have y. So it is 5, 7, so it is 0. So it is 2, 9, so it is 0. So it is 13, 15, it is 1. Okay, it is 17, 19, it is 1. Okay, so something like this. So this is the kind of the training training data that you can consider. Okay, the training data is in this form. So x1 is x2 basically your feature vector, y is the class level, the output level, and we're going to consider this. By sample, I mean one particular row. Okay, so x1 and x2 here, if you consider this particular sample, when you are feeding this particular sample, then one I'm pointing out, the x1 in your neural network is going to be 5, and x2 in your neural network is going to be 7. Okay, so when you are applying backpropagation for this sample, you first use 5 and 7, compute all these inputs, outputs from all the layers, finally compute z. So z is going to be your predicted value by this network for this sample for some values of w's and b's. Okay, which is randomly initialized initially. Make sense? So that is your z. But I do not know whether my values of w's and b's are good for me. So I need to estimate those values. So this is my error function, and here this y is this 0 value actually, with the gold standard value. I have to minimize this error. That's what I have to do. Okay. All right. So that's my objective. So before you compute the derivative, first you have to take the forward pass for the same sample or a set of sample, whatever that you can take. Take the forward pass, you compute the z values, and only then you can compute the derivative. So on. Okay. All right. So what would be this? The value of this? That's my question. Okay. I have to compute this one, and then I can generalize this whole thing. Okay. Now this is a little tricky, and I must tell you how to compute this, and then I'll be asking some questions for it. Okay. Okay. Now go back to my influence diagram picture. Okay. Now if you look at this diagram carefully, network carefully, W is here. Okay. So this W is influencing this node. Now once you are influencing this node is also influencing this node and this node. Then they are influencing this node and this node. Then they are influencing this node. So this W is basically influencing the entire this particular structure, all the tick points that I have given. Okay, because they are the W value. If you change a little bit of W, this is going to make changes to all these neurons after that. Okay, and basically I have to take into consideration that structure. And because you have seen previously that there is a common kind of structure that we find between different parameters, so we're going to make use of that structure. Okay, in a slightly tricky way. And what's the tricky way? Okay, let's first try to understand the influence diagram that I mentioned. Okay, so what is the influence diagram? And it's complex to write it down. So my E is depends on, in this case, I'm just skipping this bit. Now W is basically input to this, W is influencing input to this node. So in that sense, my E is influencing I31. I'm just writing down in a compact way. We will expand I31 again later on. Okay, so I31 is influencing E, and W211 is actually influencing I31. So this influencing this influencing this one, and this influencing this one. In a very compact way, I'm writing down. We have to expand further, coming to that point. Okay? So if I straight away apply this influence diagram into my chain rule, I am going to get something like this. So del E, del I 31 into del I31 with respect to del W2 1 1. Okay? All right. So because these expressions we'll be dealing with, I will just use shorthand notation. Okay. So this, because I have to expand this expression again. Okay, because it depends on other things. It is actually influencing other parts. So I'm using a shorthand notation for that. So shorthand notation I'm going to use is basically delta 3 1. It's for this one. So E with respect to a particular input. That's my meaning. Okay. So whenever I use this kind of notation, you will see that the partial derivative of E with respect to a particular input to a neuron. Okay. So we will basically generalize this whole thing. All right. So in a sense that, I am basically can write it down here. So del E del IL I is equals to delta L of I. Just a shorthand notation. So linguistically, it's an error change of like this values, change of error with respect to change of a particular input value to a neuron. Okay, that's the basic thing, and I have to expand that as well. Okay, all right. So this is not shorthand notation for that. Now you guys tell me what is the value of this one, this expression. You look at the top corner, you have the general expression there, and tell me what is the value of that.
Sir, output of I21.
O21, sir.
O21. O21.
Yes, sir.
Okay, is anybody contesting this? Any doubt, any problem? I mean, anybody sees any problem with that? Okay, so I think it is correct. Okay, this is correct. All right. So this is known to me. If I have to compute daily del W, this is known to me because once I have this 5 7 value here, x1, x2, and all these things is known to me. Now, but I do not know this one. Okay, this is still an unknown quantity to me, and I have to figure this out because this is kind of influencing the other part of the network, and I have to figure this out. Okay, so that is going to be my next objective, how I can figure this out quickly and conveniently. Okay, so let's take a look. All right, so I'm writing down this expression again for convenience and then try to generalize. So I'm trying to compute here del E del W211, which is equals to del E del I31 into del I31 with respect to del W211, which is equals to shorthand. This is 3 1 into O2 1. Okay, so I think what we have done so far. In general, I'm just talking about this. So in general, del E del ILI, I am denoting this as delta LI. So how much change is I'm observing in the error function if I change little bit of input, okay, to a particular neuron. So particular neuron input, how is changing that? That's basically the linguistic meaning of that. Okay. All right. Now I have to compute this guy. This important guy here. I have to compute that. Compute convenient way, efficiently. So I can compute that. Okay. So here essentially this expression. So it is del E del I3 1. Okay. So how I can compute that? Okay, all right. Now I3 is basically coming from this particular node. This is the I3. I3 means this input to this particular node. Okay. Now input to this particular node influencing the immediate next two nodes or next two neurons in the next layer. So it is influencing this particular neuron and also this particular neuron as well. These two neurons it is actually influencing. Okay, so these two way. And they are also influencing the next one, so on and so forth. But my focus would be to kind of represent this in terms of the next two layers. Okay, basically in terms of relationship, and then I can figure that out for the other one, so on and so forth. Okay, so let's focus on this particular neuron. How my input I31 is influencing that one. Okay. So how it is actually influencing that one in terms of again let's go back to our original expression. So my error function was E. So E again, E depends on input to this node. So which is I41. So I41 depends on output from the previous node. Okay, which is this one. Okay. So what is that? This is O31. Okay. And then this depends on I31. Okay. That may influence diagram. So I'm considering this node now. I'm not considering this node yet because I know the W value that I basically here I have in this particular node is influencing both these two nodes. I'm just focusing on only this node and then we will go to this second node later on. So let's focus on this one for that. So if I convert this into the partial derivative rule, what is going to happen? So it is going to happen something like this, that I have del E del, you guys can tell me what would be that? Del I what?
I41.
This is I41 into
Del I41 by del O31.
Del I41 del O31, right?
Yes, sir. Then del O31 by del I31.
Del O31 by del I31. Okay. So this is because of this. So it's just because of this particular node. Okay. I'm not done yet. What is still remaining? Still remaining the other node. This node. Okay. So plus, because this information is going through this, so plus I have to compute for this node as well. So you guys can tell me what is the value for this particular node. So node number 2. So del E and then what?
Del I42.
Del I42.
Del I42 plus into 1 minute.
Del I 42 by del 431.
Into del I
42 by del I 3.
del I what?
431.
Del O31.
Del O31.
Del O32.
Okay, sorry, I just erase one. Okay, del what? Del O3.
O31.
Yeah, because the output is going to be that output is influencing, and then del O3 1 with respect to del I3 1. Okay, so because it is influencing these two nodes, and that is my expression. All right. Now it is time to simplify even further. Okay, I just would simplify further simplification. So what is the further simplification? I'm writing down here only. So remember that I was using a shorthand notation like this. Okay. So if I simplify that whole thing, so what would be this? Tell me. Del what?
Delta 4-1.
Delta 4 1. All right. Into. Then if I simplify this guy, what would be the value?
W113.
W311, right? Okay. And what about this guy?
F prime I31.
F prime I31. Very good. It's absolutely perfect. And then plus. Then what?
Delta 42.
Delta 42 into W what?
W312.
W312 and then what?
F prime I31.
Perfect. It's absolutely perfect. Okay. So from this, what I can write down? I can even simplify further. So there's a common term, so which is F prime I31, and then I'm just writing down in a simplified way W311 into delta 41 plus W312 into delta 42. Okay, so that is basically expression for this guy, delta E, or rather it is basically for equals to delta 31, right? Okay, this pen is creating trouble for me. Sorry for this little trouble in my pen. So yeah, so this equals to delta so this guy delta 31. Okay, so is anybody disagreeing with me? All right, so you can see it how this is actually happening and so on. Okay, now it is time to come up with a general rule. Okay. So for anything, for any network, for any number of neurons, and what would be my general rule? Okay, So next, my general rule is going to be, okay, what would be my general rule? So I would like to express this one. Delta L I is equals to, okay? So because for every node I have to compute it, for all L, for all I have to do it. So I have to basically find out a general rule for that. Okay. So what would be the general rule for this, for any kind of network in terms of the number of parameters, number of layers, and everything else, and so on and so forth. Let's go back to this and try to kind of figure that out. Okay. So this is your expression. Now, can you see any simple pattern in this expression? What is actually happening? Okay. So I might use something here only so that you can kind of figure out general rule here. Don't want to use anything elsewhere. So let me just write it down here only. So that you can understand it. So what I'm trying to say, what would be my this delta Li for anything, any kind of network, anything like that. Okay, give it a try. What would be that? So this is all about back propagation that you heard of. Okay, it's the same powerhouse that we use everywhere. Can you see any symmetry, any pattern in like
F dash I.
Okay, let me just one moment. Yeah, I just write it down. F dash what?
I L I. Delta L I.
I. Okay, perfectly all right. And then what?
Summation j equal to 1 to 2.
Summation of j 1 to n L plus 1.
Summation is j is equals to 1 to
n L plus 1. N of L plus 1.
n plus L plus what?
L plus 1.
N L plus 1. Very good. And then what?
W L of ij.
W
L of ij.
W L of ij. Okay. W L of ij
into delta of L plus 1.
Delta of what?
L plus 1 j.
L plus 1j. Yeah, perfect.
Can't write the summation term as delta Li.
Sorry?
Can we write the summation term as delta Li?
Your voice is very faint.
Can we write the summation term as delta Li?
Summation is delta Li. Which one? Which summation?
Whatever thing you have written in the summation, can we write that as delta Li?
Why you want to write that in this way? I mean, do you have any? But so you want to introduce a new notation or what? Or
Okay, no sir, I got it.
yeah, I mean, because see, what we are trying to do is this. Now, if you look at this, so there is a reason for that. Now, if you look at this expression carefully, and I'm explaining in the next slide, maybe that will be clear from programming point of view why that is basically important, and you'll get to know. Okay, but this is the general rule for that. Okay, so that basically you have computed this particular expression. Okay, and you already know this one. So the derivative computation is pretty straightforward. It is just replacing this. So only factor that created problem for us was this one. So we computed this one from using this formula. I also have this one and so on and so forth. Okay, so I get it. Now, what is the reason that I want to do that? Okay, now when you're computing, you can actually compute first So delta for this particular node, what is the delta? It will be delta 6, 1, right? Then using this particular formula expression, you can compute delta for this one, also delta for this one. You can next compute that using this particular formula. You can also compute next using all these things, delta for this one, and so on and so forth. So this recurrent, you see, this is a recurrent relationship. The recurrent relationship will help you to compute delta Li for all the nodes right from back to the right to the left. Okay, and that is called dynamic programming. You are reusing these values. Once you compute the all deltas on the right side, then you can compute delta efficiently for the left side. Okay. So I will end by giving a small kind of remark in case you want to remember this expression. If you look at this carefully, this expression, this is nothing but a weighted sum of the deltas and multiplied by one additional factor, which is derivative factor. Okay. Otherwise, this is simply weighted sum. So it's nothing simple like this. So this is your, for example, delta corresponding to this node. So this node's delta will be delta of this multiplied by this weight, the delta of this multiplied by this weight. That is exactly the expression that you are basically writing down in this case. Okay. So here you have this expression only, that expression. And then only additional derivative of this particular node is coming out. So you don't have to even work it out when you are implementing. It's pretty simple if you look at this carefully. For any node, you can very quickly figure that out. Okay. So it's 9:55. I have to stop. So I will stop, and then an easy exercise for you would be to come up with similar expression for the biases. So what I like you to do is this. What I like you to do is this. Basically, this one. So del E, del B, L I. I want to derive one expression for this one only. I showed you how to compute for the weights, but I want to compute an expression for this one, general expression for this one. Okay, and we will see in the next lecture how you can do it. Okay. So that's it from my side.
Sir, I had one small doubt.
Yeah, sure. Go ahead, please.
Sir, could you go back to the before slide?
Previous slide, okay. All right.
Yes, sir. So here when we are calculating del E of del I31, we are directly adding it like an influence from node, like from the neuron 1 of layer 4 and neuron 2 of layer 4, right? Like,
right.
How, like it might be dependent on that, no, sir? Like how are we directly adding that?
It's dependent on, yeah, it depends on so that is, dependent on the neurons in fourth layer, 1 and 2, right?
Like, I mean, how are you adding this part? You're adding two parts of that function, right? So like this 3 multiplication part added with again the part of neuron 2.
Yeah. So your objection with the addition part, why you are adding this thing?
Yes, sir, kind of.
Oh, okay. So that is actually, if you kind of, so that is, so when you are actually doing this thing, actual computation, this is the function itself is addition, sum into sum into sum plus sum plus sum plus sum. So there are some components, okay, and they are added. So it is coming from directly from there. I mean, there is nothing special in it. It's just like function manipulation.
Okay, sir.
Yeah. All right. So remember that I am going to give one assignment where I will ask you to implement back propagation from scratch. And that is how you're going to learn things. Otherwise, if you use library function, you are never going to learn anything. So in one of this assignment, I'm going to give this one. With a small problem, small neural network, I'll be asking you to write down the code from scratch. So make sure that this is clear to you. This is the backbone of neural network. Okay. So everything that you do, training, etc. this. I want you to understand this very well. Okay. So yes, I will stop then. Thank you very much for joining, and I will see you next Monday. Oh, okay. So next Thursday in the lab, and then next Monday in the class.
Thank you, sir.
Okay. Thank you.